Okay, so we can begin.
Okay. Yeah. Thank you all for attending my second lecture, and good afternoon or good evening. So this in the second lecture, I will discuss infinite dimensional reduction method and in the outer grid. So in this lecture, I will explain what is inner and outer grid scheme. So let's recall in the first lecture, we discussed the finite dimensional reduction method. Also, our model problem is nonlinear Schrödinger equation, and we divide the problem into two steps. First, we solve this problem up to Lagrange multiply, finite many Lagrange multiply. And these ZJ are approximate kernels, okay? Approximate small eigenvalue, the eigenfunction corresponding to L. And in the second, so the case steps are non-degeneracy of the building block, upper estimates, and this in the outer estimate. And in the second step, we adjust lambda in the configuration space so that the Lagrange multiply equals 0. And in this step, we use a critical point theory. And so in the first lecture, we dealt with the problem of construction solution with finite many bumps. The configuration space is finite dimensional. So sometimes the configuration space may be countable for many, like Brazil first open problem, but still is a like bigger measure zero set. So in the second lecture, we generalize this idea to problem of construction solutions, concentrating on higher dimensional sets, such as curves, surfaces, or minimum surface of codimension M. As in the finite dimension case, we proceed in two steps. In the first step, we solve the problem along each tangent plane. And this amounts to imposing infinite many orthogonal conditions. And in the second step, we move the higher dimensional object in the normal direction to find a true solution. So basically it's the same idea, but with infinite many parameters now. So there are two kinds of infinite dimensional reduction for elliptic bond. The first case is the stable case, with the profile function is stable, and this is an Kahn equation, and which I'm going to do this in this course. This is a transition layer case. The second case is the resonance case. In this case, the profile function is unstable, and this is the spike case. So in this talk, I only discuss the first case. So we consider an Kahn equation. So the model problem is an equation, and it has two global solution, -1 and +1, double wall potential, and it has a one-dimensional solution connecting from -1 to +1, -1 to +1, and in fact, the solution is explicit, which is tangent hyperbolic. And we have this formally has this energy Ginzburg-Land type energy functional, and it has two global minimum, -1 and +1, and we have two global stable solutions, which is constants. And so this problem has a deep connection with the minimum surface. And in fact, if we put the Epsilon version of this problem, we consider this problem in a bounded domain, and we put a epsilon here and one epsilon here. This is just a normalization. And the solution will approach to +1 or -1, and with an interface in between. And in fact, this interface, if we compare the energy, formally compare energy, this interface is like the area. The energy is like the parameter of the interface. So formally, critical points of the uncount formally correspond to critical points of the parameter. The critical points of the parameter is mean coefficient equals 0, which is minimum surface. So this is a form argument, and this argument works for gamma convergence. And what I'm going to show you is from the PDE level how we can establish like one-to-one correspondence between these critical points here and the critical points here. Okay? And so if euphemism is a local minimizer, then by gamma convergence, the interface approach to minimum surface. And this is the gamma convergence theory of Modica, Montola, Korn-Sternberg, and Caffarelli and Cordova prove C1 alpha estimate if shown is a graph. And Hutchison and Tanagara prove the quantization. Tanagara and Kara prove the stable solution for C1 alpha estimate for stable solution. And Wang and myself will prove the C2 alpha estimate. And later, at the end of the lecture, I will see how we can use the reduction method, the infinite dimensional GUI method, to prove the C2 alpha estimate. And there's also an interesting correspondence between minimax theory of Arlen-Kahn, Ruslandic Shannon theory, and the corresponding minimax theory for minimum surface. And this is explained in Gaspar and Garacco, or Chordish and Montanitis. All right, so this is the background about this Arlen-Kahn equation. This is the equation I'm going to consider now, this Arlen-Kahn equation. So it has deep connection with minimum surface. Formally, in the critical point level, you see minimum surface. And so in this lecture, I will describe a precise correspondence between three-dimensional Arlen-Kahn equation and embedded minimum surface of finite total curvature in R3. So in this lecture, I'm going to show you this is simple OD PD, very simple PD, but contains the whole theory of minimum surface in R3. This should be 3, sorry. So I'm going to show a one-to-one correspondence. And the one-to-one correspondence is achieved by the infinite dimensional reduction. So let me first give you some background on minimum surface in R3. So let M be a completely embedded minimum surface in R3 with a finite total curvature. So which means the fundamental form is integral of the fundamental form is finite. For minimum surface, the Jacobi operator is Laplace binomial H plus A square. Because the underlying is R3 Euclidean space, so no Ricci curvature, and the kernel of this Jacobi field, the bounded kernel for this Jacobi field, are called Jacobi field. Okay, the bounded kernel for the Jacobi equation, Jacobi field, and for minimum surface in R3, you have at least 4 Jacobi field, 1 translations and rotation. The other 2 rotations you can change it to other. So you have at least 4 kernel, okay, for the Jacobi operator. And we assume that M is non-degenerate if these are the only 4. Okay, these are only 4 kernels. So, and there's a lot of important question has been answered for this minimum surface. So the examples are Costa Catenoid. Okay, this will be our example, and also the Costa-Hoffmann mixed surface, which has more holes. Okay, in the middle. So the main result I'm going to present is a result with Manuel Pino and my colleague in 2013, so 12, 13 years ago. And so that n equals 3 and m be a minimum surface, embedded minimum surface, which is non-degenerate. So the result is the following. There is a final solution to the Yannick equation such that the final solution, the node set of the final solution, is almost like the minimum surface, but enlarged with scale the minimum surface. Okay, so the node set is like m over alpha. Alpha is so small, and furthermore, U is non-degenerate. So the only kernel are given by translation and rotation. And we can also prove the index of M, which is the index of the Jacobi operator, equals the index of U, the Morse index of U. So we have now a one-to-one correspondence between this Yannick equation and the minimum surface in R3. And we have all information, including the spectral information of minimum surface, can be passed to the solution. So this is the, I want to explain the idea of the proof of this theorem. And this is at the beginning of this infinite dimensional reduction. And it has many, many applications. Okay. So the proof consists of 7 steps. First, we studied the property of the building block, which is the tangent hyperbolic function. And second, we use some geometry. We established the Fermi coordinate, okay, on minimum surface. And then we found the first approximation and the first improvement. And the part 4 is the most important one, is the inner outer green. So how we reduce the problem into inner problem and outer problem. And we solve the inner problem by infinite dimension reduction. And then we solve the outer problem by Jacobi operator, by theory of the Jacobi operator. And finally, we have the proof. We have the including the Morse index. Okay, so let's start with the building block. The building block is the tangent hyperbolic function, and is exponentially decay in approach to -1 and +1, and is stable. So the first eigenfunction is 0, and is given by translation, and the second eigenvalue is positive. So the profile is stable. Okay, it's a stable profile. And we have this a kind of a spectrum gap estimate. So this is very easy to see. Very easy to see. Now, we need to lift this profile to 3 dimensions. So we need to add 2 more variables. Okay, so we have this t variable here, but we need to add 2 more variables at the Laplace. And so we need to look at this linear operator with the whole Laplace in R3. So whole Laplace R3. And we need to see what are the kernel for this problem, for this lifted, okay, for this lifted linearizer problem. And the result is the same. It's a 1 dimension. So for the lifted problem, again, the bounded smooth solution, just translation. So this is the non-degeneracy of the 1D solution. 1D solution. But this 1D solution is in 3D. So how to prove this? So we prove this by spectrum estimate. So suppose we have bounded kernel, and first we prove that this mass has exponential decay away in T, okay, away from the interface, uniform UI. And here we use we use the barrier. Okay, we use this type of barrier function, and we can show that the solution is exponential decay away in time in t. So with this exponential decay, then this function, so we integrate in the t direction, the L2 norm is well defined. Because at the beginning, we only assume it's bounded. But now we show that the solution actually has exponential decay in the t direction. So we can do L2 norm in t direction. And this is the point. So we enter this function. So we decompose our phi for each y. We decompose the phi into direction of w prime and the direction of orthogonal to the w prime. And we for the orthogonal part, and we computed the Laplace, and we integrate. We do integration, and we found that this is non-negative. So the Laplace of this is non-negative. But phi is non-negative. So phi, by maximum principle, phi must be 0 because this is a Schur harmonic function and is non-negative. And so phi can be decomposed into w prime times some function. And this function turns out to be a harmonic function in R2. So the only solution is constant. Right? So this gives the proof. Okay, so this part is relatively easy because our problem is stable. Now for the spike case, then we have to do more estimate. Okay. Now in the second step, we introduce the Fermi coordinate. So we take a minimum surface M. So we enlarge the minimum surface. We fix the minimum surface, but then we rescale. And for this minimum surface, we look at a normal perturbation of this minimum surface. So now we have now we have a new function h, which is undetermined. And so on each point on the surface, in the normal direction, we have a normal perturbation. So h of y. And so this is the new coordinate. This is the new coordinate we're going to use. So this new coordinate, of course, this is a surface. This is the minimum surface. So you have to do a chart. But you can compute the Laplace in a local chart for this new coordinate. And this is a very simple-minded computation. So what we found is the Laplace in the original variable equals dtt, so it's the normal direction, plus Laplace Bertrand operator on M alpha. And then you have alpha square of the Jacobi operator. Jacobi operator is here. And this is a translated Jacobi. And then we have mixed order terms and higher order terms. So the reason that we don't have alpha term is that we work on a minimum surface. So if your surface is not minimum surface, you're going to say alpha times the mean curvature. But our mean curvature is 0. So we don't have the alpha term. Okay? So we have the minimum alpha square term. And this is the Jacobi operator. So it's your perturbation of the minimum surface in the normal direction. Okay, so now we put our first answers, the W, okay, T is the distance to the minimum surface, and we'll plug this one in, and we're going to add this mean curvature term, this fundamental solution, this part, because I want to kill this part. We want to kill this part. Okay, to kill this part, we modify our ansatz, this A square. Okay, this second fundamental form, and we plug this in, and we get a new error will be alpha cube. Okay, and exactly we solve this. This term we kill this A square term. Okay, we kill this and so the new error is like alpha cube and 1 plus r minus 4 and e to the minus sigma t. Now let's remember this is the distance to the minimum surface, right? And this is the decay along the minimum surface, because our minimum surface is unbounded. Okay, is so we have an algebraic decay in along the minimum surface, right? And we have orthogonal exponential decay in the orthogonal direction. So this is our error, and we're going to work with this type of error. Okay, we're going to work with this type of error. All right. So okay. So now we introduce the ansatz, the profile, the Fermi coordinate, and the first approximation. Okay, and now we want to find a true solution. Okay, we want to find a true solution. So here is the main idea, the inner outer green. So we look for a solution of the Yannick equation in this form. And U equals W. W is the one we introduce. Phi is the error. Okay, this is the one we want to find. We decompose this error into two parts. Okay, into two parts. We have a cutoff function. This cutoff function is near the minimum surface. Okay, is defined in a tubular neighborhood of the minimum surface. And this function here, the red part, defines in the whole space and is defined in the rescaled variable. And the psi is the outer problem. Is everything remained, is psi is the outer problem. Okay. So let me repeat. We are looking for one function, but we decompose this function into two functions. So one function has a fast variable here, and the rest of this has a slow is the original variable. Okay, and this is the cutoff. So now, what is this function? This function we call the inner function. This function is called the outer function. And so for the inner function, we construct an inner function satisfy the inner and this phi and the psi satisfy the coupled system. So the coupled system, what we do is we chalk, because our Fermi coordinate only defined locally. So we have to cut off everything in locally, and we just extend it to 0 outside. So we have now a inner problem which is defined in M alpha times R. So it's defined everywhere, like a cylinder. Okay, and this is our first error here. And for the outer problem, we do the following. We put one part of the outer problem in the inner part, and we put the rest of the problem, rest of this in the outer part. So this is the inner outer component. And here, so the inner problem enters into the outer problem by the cutoff. There's a cutoff here. So the blue part is the inner to outer. The red part is the outer to inner. Okay. So what we have done we have one equation, but now we decompose it into two equations. And so this has an inner equation and this is the outer equation. So we need to find this coupled system. So these two problems are coupled because the inner part appears in the outer part appears in the inner part. Okay? So this is the inner outer grid. Okay? This is the inner outer grid. So basically, we reduce the problem into one problem. We see the m alpha times r, which is defined in the cylinder, and here this one is defined in the whole R3. Okay. Okay. So how to solve this coupled system? And we solve this coupled by the following. We fix the phi in some topology, and we solve the psi. And then we plug this psi into the inner problem. Then the inner problem become a non-local problem now. Okay, so this is the whole. So the outer problem enter into the inner to this fast decay. Okay, and the inner enter into outer to the cutoff. Okay, and so base operator is this inner problem, and which is and the base operator for the outer problem is like a Bessel. Okay, so this is the coupled region. So the coupled region somewhere, this is the surface here, the minimum surface. The coupling is somewhere here. This is the inner and outer. The information between inner and outer is flowed through this coupled region. Okay, this is the coupled region. So this is the inner outer grid. Okay, so using the Fermi coordinate, we can write the inner problem like basically like a Laplace operator and plus perturbation terms and this f prime and the error here. And here we have the outer to the inner, and here we have the nonlinear terms. And the first error is already almost like alpha cube. Okay, the rest is the alpha square times the Jacobi operator in the normal direction, and the rest is alpha cube order. Okay, so and remember our error is alpha cube. Okay, alpha cube 1 plus alpha r and 2 minus 4 e to the minus sigma. Okay, so for the inner problem, the norm we're going to introduce. So now we're going to introduce various norms that are tailored to the inner and the outer problem. So inner problem, the error is like this, which has fast decay in t direction, exponent decay, and algebraic decay along the surface. So our norm captures this error. So our norm, the norm has exponential decay in the normal direction and algebraic decay in the tangential direction. So this is our norm. Okay, and we have to use W2P local norm because the B term here contains lots of second order derivatives. Okay, there's lots of second order derivatives in the B term, so that's why we have to use the W2P theory. Okay? W2P theory, and later we use the C2 alpha theory. Okay, so for the outer problem, so we have for function defined in the whole R3. So for outer problem, we just need to decay in along the surface. Okay, so this is the problem for on the surface. This is a problem on the surface. Okay. And and what about the normal direction, the edge? So the edge we use decay, right? We use the algebraic decay and the W2P norm. Okay, use algebraic decay and the W2P norm. Okay, so this is the first step. So we decompose the problem into inner and outer problem, into two problems. Okay, this is a coupled system, the inner problem and the outer problem. So now we need to solve the inner problem and we need to solve the outer problem. And we define all this norm. Okay, so to solve the inner problem, we solve the outer problem first, which is easier because the outer problem we already cut the profile near the interface. We cut the profile near the interface. So the outer problem is really look like Laplace minus 1. Yeah? It's looking like Laplace minus 1. But with this in the outer green, with these cutoff functions. So if we get an inner solution which decay in both in T, exponential decay in T, and algebraic decay in R, then this coupling term is exponentially small. So then by the rectangular theory, we can get I map you fix a phi, you can find an outer problem which is exponentially small. Okay, which is exponentially small because of the outer, because of the cutoff is in this region. Okay, in the coupling region, the phi is exponential decay, and also this map is Lipschitz. So you take a different phi one and phi two, and this coupling, the outer problem is Lipschitz. Okay. So we can solve the outer problem. Now we replace the inner problem by this outer problem, by this outer. So this outer depends on phi, but the dependence is non-local. It's a non-local dependence, and so we have rest the non-linear terms. So now we have uh, to find a solution for the inner problem. So now we already solved the outer problem. We suppose the outer problem can be solved in terms of the inner problem. And so we have we put all this the coupling from outer to inner in this part because this is really small. Okay, so this is the problem now we need to solve. Now we're going to use infinite dimension reduction to solve this new nonlinear and non-local problem. So, and step 5, now we solve the we do the infinite dimension reduction, right? Just like in the first lecture. So, we for any fixed function h, so we perturb the minimum surface in the normal direction by h. So fixed function h. So this is a function. Fixed function h. We can find two functions phi h and ch satisfy the following. And this is the inner problem can be solved up to the Lagrange multiply, but this Lagrange multiply is a function on the surface, right? So it's C of y w prime. This is a functional. Okay, this is a functional, and so we're going to so for this function, and we impose for each y on the interface, for each y on the minimum surface, we impose I was organic condition in the normal direction. So here we have infinite many solutions. infinite many, conditions, right? Here we have infinite many conditions. So this is the infinite dimension reduction. So in the first lecture, these are finite many numbers, okay? But now this is a function. And so this is the first step. Now in the second step, we want to find a true perturbation of H so that this C is 0. So you see that this is a similar idea as in the first talk. First talk we fix many points. We found many CJs, and then we put on we want to find the points so that CJ equals 0. But now we fix a function. We fix a function. We found another function, and then we want to perturb this function so that this Lagrangian multiply, this is Lagrangian, this one equals 0. Okay, and it turns out this is we use the inner outer green to do this, and this one we use the Jacobi operator, okay, to solve this problem. Okay, so let's solve the linear problem. So the linear problem now is again always the key point to solve the linear problem. So we take the linear problem here, forget about all the nonlinear terms. We solve a J here, G of YT here, and we want to find a C and find a phi so that this can be solved. Okay, so similar to the first lecture, suppose the problem can be solved, we can get a C in terms of G. Actually, the C is just the perturbation, just the projection of G in W prime. So this is C. Okay, this is C. So now we need to find the phi. So in order to solve the projection linear problem, we need to devise a theory to solve the problem where we consider the class of right-hand side G with quantitative behavior, similar to the error S of U1. And this is the typical type of error, okay? And we're going to work in this type of right-hand side, okay? And this is the key estimate. So we assume that G has this property. Then we can find a unique solution phi with this decay in the exponential decay in the normal direction and algebraic decay in the tangential direction. Okay, and we have this also this estimate. So this is the upper estimate. Okay, this upper estimate we need to find. So how to get this prove this upper estimate? So once we have this upper estimate, then we're done. The reason is because I can solve this problem in a big finite. We cut the minimum self. We solve the problem in a big ball. We put the zero boundary condition here, and differential boundary condition. And if we can have similar upper estimates for this problem, then we can just use the freedom alternative to solve this problem. And we solve this problem up to this Lagrangian multiplier. Okay, so now the problem is to get an upper estimate for this problem in a big ball, but with a differential boundary condition. Okay, so this is the key upper estimates we need to have. Okay, so let's assume C equals 0. First, by local elliptic estimate, we just need to show that L infinity norm can be bounded. Okay, and we prove by contradiction. So suppose L infinity norm, we don't have the boundedness of L infinity norm. So we can find a sequence of alpha n go to 0, and R with the ball, Rn go to infinity, Gn with this norm go to 0, and phi, the L infinity norm is bounded. And we have this equation. Okay, so what is the phi L infinity norm? Phi the L infinity norm is this one, is this norm. Okay, we have, so this norm is bounded, is 1. Now we want to get a contradiction. Since this weighting norm is bound is 1, we can find a points y and tn so that this is greater than equal to half. So this is the algebraic decay, right? This is the exponential decay. Okay, and this should be plus. So this should. So we consider 3 different possibilities. First is this number is finite. If this number is finite, or this number go to infinity, or this number close to the boundary, or this away from the boundary, or close to the boundary. So these are the 5 cases we need to consider. So let's first consider the simplest case. We consider the points. So this point where we take a limit, this point does not go to infinity. Okay, and you say a limit, and this limit is a limit on M, on the original M, because this you already rescaled. So at this place, and you do have a chart, and you do a chart, you compute the Laplace. Okay, and this is simple computer Laplace. And now in this case, we discuss 2 sub cases. So first we assume that this is bounded. But what about Tn? So this Tn can be bounded or infinite. So let's assume that Tn is bounded. And we just do rescaling. And you do rescaling and do compute the limit. And what you get is this limiting equation, but with this coefficient, and this coefficient actually is a constant coefficient, constant matrix. So and you by rotation and stretching, and this will become just Laplace. Now by the non-degeneracy result, we have that this is a C double prime, but we have this orthogonal condition, right? We have this orthogonal condition. So phi tilde must be 0. And this is a contradiction because we assume that this is greater than equal to half. Okay, so since Tn and R are both bounded, then this is the simple case. So this is the simplest case. The simplest case is the points stay bounded and the T stay bounded. So locally you see some bump, but since your solution is orthogonal to this, since you have a non-degeneracy, and this cannot happen. Now the second case is this Tn go to infinity. So in the normal direction it goes to infinity. So in the normal direction it go to infinity, and what you do renormalization, and what you found is again is a Laplace equation, but with a convection term. This is a small convection term. So, and since T goes to infinity, this go to 0, go to -1 or +1. So you get a linear equation with convection term. And as long as this convection term is small, maximum principle tells you this cannot happen. Okay? So now the second case is this points alpha n, yn go to infinity. In this case, then we have a chart at the infinity for the manifold. The chart at the infinity, you can, okay, you have to rescale because we have algebraic decay. So we have to rescale everything by the algebraic decay. And you take a limit, and again, you're going to see that a same type of Laplace equation linearized Laplace equation and with this bounded with this also analytic condition. Okay. Now, what about when the points approach to the boundary BR? If the approach to the boundary BR, then you get a half space problem. But we have a differential boundary condition, and you just by extension, and you get a contradiction. So I will not do this. The whole argument. So the whole argument you have to consider many cases, but each case you can exclude either by non-degeneracy or by uphill maximum principle. And once you have this, then you have existence. This is the freedom alternative. So because for each R, I have uphill estimates, so I can put this problem in terms of a freedom of Ricci represent. I can use the Ricci representation theorem, and I can use just Milgram, next Milgram theorem, and we can get the solution. Right, and once you have L infinity estimate, then by local elliptic you get all the estimates. So I will not discuss this. Okay, so fine. So we have the linear problem can be solved, and then the nonlinear problem by the contraction mapping you can have a unique solution for the nonlinear problem. This is very easy to do. So finally we have a reduced problem. So the second step, we need to solve the reduced problem. So we need to find the H so that the C equals 0. And we found the asymptotic behavior for H. It turns out the asymptotic behavior for C is just the Jacobi operator in the normal direction. It's exactly the Jacobi operator in the normal direction. So what we get is I perturb. We have a Jacobi operator equals GH, okay, which is small gh. Okay, so we're almost done, except the Jacobi operator cannot be solved. Because we know the Jacobi operator has 4 kernels. Okay, so now we have to do finite dimensional reduction again. Because this guy has a 4-dimensional kernel. So we solve the problem with 4 additional Lagrange multiply. Okay, we solve the problem with the 4 Lagrange multiply, and we use the finite dimensional reduction method. We can solve this problem, and so in the end, we solve this problem using the theory of the Jacobi operator. And in the end, what we found is a solution to the Yannick equation after 4 Lagrange multiply. With this 4 Lagrange multiply with this right-hand side. And now we have to use the invariance of the Yannick equation to show that this 4 Lagrange multiply equals 0. Because in reality, and they are 0, and this is because of the invariance, okay? Invariance of the problem. In fact, the Yannick equation, this Yannick equation is invariant under translation and rotation. So using this invariance, and you can get this all this C, the Lagrange multiply equals 0. So and this proof the existence. So the whole procedure, you use the infinite dimensional reduction method and reduce the problem in the normal direction, which become a Jacobi operator. Now you use all the techniques for the Jacobi operator. And what about the Morse index? This is a non-computation. One direction is easy to prove. This is greater equal to the index of M, because each negative direction or in the Jacobi operator produce a negative direction for the Yannick. Okay, so this part is easy to prove. And to prove the reverse part, we have to show that the eigenvalues are actually it's very small, and it's like an Epsilon square. And we use the infinite dimension reduction to show that for the eigenfunction is also has this separated form, and this is a lot of computation, so I will not show this. Yeah. So what we prove is one-to-one correspondence. We use the infinite dimension reduction, and we prove that for each embedded minimum surface in R3, non-degenerate, and we prove the existence of a solution to Anacon whose node set almost like rescaled, okay, minimum surface node set, and is the solution non-degenerate, and the index are the same. The Morse index and the index of the minimum surface are the same. So let me summarize the infinite dimensional reduction method, and then I will discuss the applications. So this inner outer Green scheme is an efficient method in dealing with high dimensional concentration phenomena. So the upper estimate has two parts: the inner estimate and the outer estimate. The outer estimate gains regularity than the inner problem. To solve the reduced problem, so many new techniques from differential geometry, from Jacobi can be used. So here we discuss the coordination 1 case, which is the minimum surface. And so recently we also generalized this to coordination 2 case, which is the Yang-Mills-Higgs. I don't have time to discuss, but the papers are on my website. So for Yang-Mills-Higgs, is what we prove is almost similar here. That if you have minimum surface of coordination 2 and it's non-degenerate, then we can construct a familiar solution to the Yang-Mills-Higgs and to the Yang-Mills-Higgs, and the index are the same. Okay, the index for the Yang-Mills-Higgs equals the index for the minimum surface of coordination 2. Okay, so this is the inner outer scheme. So this is our Anacon equation, and we decompose this problem into inner problem and into outer problem, into 2 problems. And we solve the outer problem first. We assume we have a solution for the inner problem, and we solve the outer problem. We put the outer problem inside the inner problem. So we're reduced to solving problem in the inner problem. And the inner problem, we do 2 steps. We do first the infinite dimension reduction, and then we reduce the problem to the Lagrange multiplier, which is a function. And for the reduced problem, we use the Jacobi operator, use the differential geometry to solve. So this is the whole procedure of the inner outer Green. Very now is very standard now. So let me now give you some applications of this inner Green. First is the de Giorgi conjecture and the classification of global minimizer, and higher multiplicity interface, the Jacobi total system, and the C2 alpha estimate for interfaces. And this is the reverse Green method. First application, this is a well-known de Giorgi conjecture that U be a Anacon solution to Anacon with monotonicity in 1 direction, then U is 1 dimension. So this is proof in dimension 2 and dimension 3, and in dimension 4 and 8, under some conditions, under this additional assumption by Savin. And we prove this counterexample. And so in fact, the inner outer Green is in this paper. is first appeared in this paper. Okay, so the proof of countersum is based on the Bambier-Diciotti minimum graph, and so we have two main ingredients. First, infinite dimensional reduction, but the main difficulty is the Jacobi operator for this minimum surface, the minimum graph, and because this f grows like cubially, like grows like r cube. So the Jacobi operator is very, very degenerate. And so we need a global estimate for the Jacobi wave operator and this. But in general, it just follow from this reduction method. And this is Jacobi Bambier-Diciotti. So now we have monotonicity. The next is the global minimizer. So monotonicity implies global minimizer. And Safan action proof in dimension n less than 7, global minimizer must be one dimension. So there's no additional assumption for this. And in dimension 8, we prove that we have a local minimizer stable solution. And later we prove that actually we can find a global minimizer in dimension 8. So this is the optimal result, give you optimal result for dimension 8. So for global minimizer, now we have a complete solution. Because n equals 7, all solutions are one dimension, n greater than 8, and we have a counterexample. And the key idea of the proof is use infinite dimensional reduction to transport the geometric information of Simon's cone to saddle solutions of Allen cone. And so again, here the main idea is the reduction method, is the inner outer grooving. But the inner outer grooving is coupled with the foliation, of the Simon's cone. So this is the first application, the Diciotti conjecture and the global minimizer. The second application is the Jacobi total system. So the inner outer grooving can be applied and give a new proof of this Fourier theorem due to Poincaré and Ricci in 2001. And so if you have a non-degenerate minimum submanifold on M, you can construct a minimum surface concentrated on this non-degenerate minimum submanifold. And Hutchison and Tanagawa and Wickermasakara, they prove that if the energy is bounded, then the energy is quantized. So the energy is an integer of the minimum surface, the area of the surface. Okay, and the Poincaré and the Ricci case is multiplicity 1 case. So the question is, can we get multiplicity 2? And the answer is yes. And it turns out that on the Riemann manifold, so there are solutions with higher multiplicity interface. And this location of the interface is purely governed by Jacobi total system. And we derive this Jacobi total system by the scaling, by the reduction method, by the grooving method. So assume we have a closed non-degenerate embedded minimum surface, and we assume that the second fundamental form plus the Ricci capture is positive. Okay, and then we prove this result with Depino and Mike, Krasik and Junyang in 2010. We prove that we can find a sequence of epsilon I, and for any k greater than 2, you can find a solution to Allen cone with k transition layer. The mutual distance is epsilon times log epsilon. And the near issue the interface, it can be approximated by this k layer of interface, uh, and and this function fj, they certify the so-called Jacobi total system, and this is the Jacobi total system. And so we derive this Jacobi total system by the reduction method. Okay, but this is Jacobi total system by the reduction. So how to solve the problem? This is Jacobi total system. And so here we have a resonance condition here, because this Jacobi total system is highly unstable. And so this instability will resonate with the instability of the total system. And so here we use some kind of resonant condition, and this is a similar idea appeared in the McKelvey and the Montenegro and many other papers. And so the idea, so to derive the Jacobi total system, we use the GUIN, we solve the projected problem, and then solve the reducer problem, and the derivation of the Jacobi total system purely from this reduction. So if you look at the first, if you look at k layer, and you do the error, okay, you compute the error, you found that the mean curvature, okay, and you found the interaction of the layer. And so the interaction, so you have the mean curvature, you have the interaction of the layer. And so if we project everything to the minimum sum manifold, you get this Jacobi total system. Okay, to solve this Jacobi total system, we use like a resonance condition. We use sort of we solve this algebraically, and then we use a resonance condition to overcome the small eigenvalues. So I will not discuss this. There's a gap condition and so on. Okay, so this is the GUI method for the resonance case. Okay, I will not discuss this because it's very complicated. So we discussed the GUI for the stable case. Now for the GUI for the unstable case, we have to use lots of resonance condition and wires formula and so on. So I will not discuss that. Okay, so let's consider general Jacobi total system. General Jacobi total system, and we can using the resonance condition, we can solve the problem. Okay. Now the third application is the C2 alpha estimate. So for stable solution for Anna-Kahn equation, Caffarelli and Cordova prove the C1 alpha estimate for Lipschitz graph, and Hanegara and Wickamasakara prove the C1 alpha estimate for stable solutions. Okay, and so then the question is, can we get C2 alpha estimate for stable solutions? So for Lipschitz graph, we have the C1 alpha estimate, and for stable solution, general case, we also have the C1 alpha estimate. And with kind 1, and we prove that this is possible, and get a C2 alpha estimate. So if we have a stable solution to the Anna-Kahn for the rescaled Anna-Kahn in a unit ball, and the rule set, suppose the rule set is C1 beta, okay? This is already proved by Tanegara and Wickamasakara. And for dimension n less than 10, we found C2 alpha estimate. So we can go from C1 alpha to C2 alpha. Okay? And we have this condition 10, n less than 10. and this condition is optimal. Okay, so to the proof of this is based on this capture estimate in this paper. So as a consequence of this result of this paper, I mean actually this was this one is before that we can classify what the final most index of Anand-Kang. We can show that the final most index solution for the Anand-Kang must have finite many ends. In other words, the energy is bounded. The energy is bounded. So and from the theta alpha estimate actually implies the capture estimate. Okay, capture decay estimate. Okay, so we prove this in dimension 2, theta alpha estimate in dimension 2, and the Childish and the Mantonidis extended this in dimension 3, and then using this, they prove the multiplicity 1 conjecture in dimension 3, and the multiplicity 1 conjecture of Marcos and Leffers in dimension 3. Okay, and this dimension 10 in this estimate. Okay, so for dimension less equal to 10, we get a theta alpha estimate. And this dimension 10 is optimal. And if n greater than 11, so Agudano, my former postdoc, and Depino and myself, we constructed a stable solution with multiple layer. And once we have this multiple layer solution, then it means that we don't have theta alpha estimate. So, and the reason is for n greater than 10, the total system becomes Newell, and the Newell has a stable solution. So we use the stable solution for the Newell in dimension 10 or higher, and plus the Green method, and to construct a stable solution in R11 and with a multiple layer. Okay, so let me now explain what is why the stable solution for the Newell is related to the theta alpha estimate. Because the theta alpha estimate seems purely a local regularity. Right? Theta alpha estimate of the minimum surface of the nodal solution, right? The nodal set. The theta alpha is like a local condition. This how this local condition is related to the Newell, okay? The Newell solution, the total system. So if we take F and we do a rescaling, we take a solution to the Newell and we do some rescaling, and for number small, we show that there is a two-layer solution which is stable, okay, which is stable. So, and it turns out that the existence of this two-layer solution implies that you don't have theta alpha estimate. Okay, you don't have the theta alpha estimate. So, on the other hand, we show that the theta alpha estimate is equivalent to the existence of a stable solution for the total system. So how do we show this? So if we have a stable solution and if we have multiple layers, how do we extract a total system from this multiple layer? How do we do this? How do we extract a total system from this multiple layer? And the idea is the reverse Green method. This is a reverse Green method. So suppose we have a capture bound, since we have 7 alpha, we capture bound on this on the nodal set. So locally the nodes that can be arranged in these graphs. Okay, and we'll prove that the interaction between different interfaces is given by the Jacobi-Toda system. And to prove is use the reverse Green method, reverse infinite dimension reduction method. So, okay, so let me explain this. We use the infinite dimension reduction method to prove the existence of a solution. So now we already have a solution. Now we want to use the reverse infinite reduction method to prove that the interface must satisfy the Jacobi-Toda system. Okay, and so we use the inner-outer Green in a reverse order. We already have a solution to the Yannick equation, and in order to get estimate on the left side, we get good equation satisfied by this left side is needed. As in the infinite dimension reduction scheme, we decompose the problem into inner problems and outer problem. And for inner problem, we decompose the Yannick equation into the one on the left side, which is on the kernel space, another one on the orthogonal space. So this is the step 1, and this is the step 2. And to get for inner estimate, we show that the inner estimate can be estimated by the outer estimate by a small number, okay, A, and then we show that the outer estimate can be estimated by by B times the inner estimate. So we are doing everything backwards. So we're doing the inner estimate for the inner problem by the outer, and the outer problem for the inner, and then you prove this together, you get reverse in the outer Green, and then you get the decay estimate, you get the reduced Jacobi-Toda system. Okay, so as a result of this reverse Green, now we can say the obstruction to C to alpha is reduced to the total system, to existence of the stable solution of the total system. So by this reverse Green, we reduce the graph, the equation for the graph to this total system. So if this total system, the distance between this, if they are too far away, then we don't see these guys. Then this is too small. This is too small. Then we have Laplace equals very small number. Then we have C to alpha estimate. So the question is, if we don't have C to estimate, then one of these guys should be large. If one of these guys is large, then we can develop procedure, and then we found an entire solution for the total system, and the stability of the Yannick equation can be passed to stability of F, and the stability of F can be passed to stability of total. So now we have a stable solution for the total system. Now, and so we proved that the obstruction to the C to alpha estimate is the existence of a stable solution for the total system. And we show that when n less equal to 10, there are no stable solution for the total system. And when n greater to 11, then there is a stable solution for the total system. So, and this gives the proof. So what I discussed today is the infinite dimensional reduction method to prove the existence for the Yannick equation, and we use this reverse Green and to prove the C to alpha estimate. And many applications of this infinite dimensional reduction method to elliptic problems. And as I mentioned, there was a recent application to higher coordination minimum surface for Yang-Mills cakes, U1 Yang-Mills cakes. So and this is the end of my lecture today. Thank you. Are there any questions?
Yes, so in the main proof, I just wanted to understand the significance of making the choice of using the Fermi coordinates. So where exactly, how significant was the use of Fermi coordinates in the proof?
Yeah, the Fermi is very important because you know we're used to the to the Euclidean, right? But now our underline is minimum surface. So we need to establish a coordinate near the minimum surface. And the coordinate near the minimum surface, we have to single out the distance function, which is the t. So basically, any point near the interface, we can project to the interface, and then the distance to the interface, right? So you can this y and the t, and these two coordinates are orthogonal to each other. So locally it should look like a cylinder, like m times r, and yeah, and this is a very, because you see from the Fermi coordinate, you see the Jacobi operator, and the Jacobi operator comes from the Fermi coordinate.
And this Jacobi operator associated to this Alenkane equation is always stable?
No.
Initially you mentioned it's like the example of
okay, all minimum surface in R3 they're unstable except hyperplanes. So they all have index. So the solution we get here, the index is always greater than 1. And
so stable, you mentioned when you mentioned the examples. So there were two distinct examples when you began. So one was Alenkane equation where you mentioned it's like associated stable. So what is stable captures there?
or the stable, this is dimension 3. The stable is in R8. Stable solution for Alenkane is in R8. Yeah, the stable solution for Alenkane is high dimension. Is R8.
And just one more, can you please define what is resonance? Is the word used? What is resonance?
Okay, I don't have time to discuss.
Okay.
So at this moment, we discuss the Alenkane, which is stable. But if we do the Jacobi total system, then this system will have resonance. And because this guy has unstable eigenvalues, and this unstable eigenvalues will interact with this nonlinearity. And so you have to choose a special resonance gap in order to invert this problem. Otherwise, you cannot invert this problem. So there's a resonance come from here. This is a resonance problem.
Okay, so thank you and see you tomorrow.
Yeah, thank you very much for staying so late for the lecture. Thank you.